know that it doesn't really give us numbers, but I can still explain it on how we can solve it. Sorry. So we were using conservation of energy again, and we will draw the different diagrams that will occur, and we have to show that we take the potential energy of the bucket, right, which will probably be zero, right, because it's the potential of the bucket with the Earth system, so it's going to be zero, and the bucket's at water level. When the bucket's out, I'm sorry. And the bucket's going to have initial potential energy, and it's just going to be the final value of is going to be zero, the potential energy. So we know that the initial kinetic energy, Ki, is going to also be zero just before the impact. The bucket is going to be mass, which just multiply each other. And it's going to have a kinetic energy of mass times velocity, and the rotating cylinder has a kinetic energy as well. So we got to keep a track of all these different things. So let me just write down the different equations we're going to use. So we're going to be using 0 plus mgh. It's also going to be equal to 1/2 mv squared plus iw squared. This is what I was explaining earlier. Maybe it was easier to write it out. And we realize this, right? And we just have to plug in our numbers, and it's going to give us our velocity. And then we have to replug in our velocity to be able to find the work and the angular velocity. And that's how we're going to find the angular velocity when it hits the water. It's kind of complicated if you don't understand it, of the conservation of energy. But you just got to remember that these are the basic equations. So 0 plus mgh is going to be equal to the 1/2 mv squared plus 1/2 of iw squared. Then you basically find the answer. Okay, thank you.